So inverse functions. Let's take a simple example. Okay, here we go. Let's take a simple example. F of x equals 2x plus 3. Okay, so this is a nice function. It's like the demand, and I know that most of you really know how to take the inverse of it. But let's dig a bit deeper. So what is happening with this function? So what does the function tell us to do with x? So the function saying, you take x, then you add 2. So the result that we obtain is 2x. Then the function is telling us, no, it's not add 2, it's multiply by 2, sorry. Multiply by 2. The function tells us multiply x by 2, we multiply. Then the function tells us, okay, perfect, you obtained the result of 2x. So let's put it in a different color. So it's all nice and you understand what's what. Blue, I like blue. So then we do 2x, so that's what we obtained. Perfect. Then the function tells us, okay, all good, now add 3. 3, we get 2x plus 3. Okay, perfect. So as I tried to explain last time, inverse function will undo this process. So the f minus to the power of minus 1 of x will be, wait, we don't know what will it be, but let's imagine. So the inverse function will tell us, okay, take your x, perfect. Now, subtract, am I spelling it correct? Is it subtract? Thank you. So, subtract 3. And then divide by 2. So after subtracting 3, what we get is x minus 3. Then we divide the whole thing by 2, and what we get is, actually that's going to be a fraction, so x minus 2 minus 3, sorry, divided by 2. So again, I started from the end, so from the very last operation that we did. And in this case, wait a second, after subtracting 3, we get 2x, no? No. So now what I'm talking about is not this function anymore. I'm talking about the inverse. So how can we find an inverse using some different logic? And if we say, okay, that was this multiplying by 2 and adding 3, that was the algorithm that function f provided us with. Now we want to understand what does the function f to the power of minus 1 have to offer. So it will be an inverse and the function will be okay. The algorithm is the following. You take x. We could take actually another letter here. So we could take y, for example. But it doesn't matter because, you know, I explained to you last time that in the notation we use x again. So for the Fahrenheit Celsius we switched letters, but here we can use the same x. It's really up to you. I really could do here, I could say y. Doesn't matter. But if I do it with x, you really see that we're dealing with the same variable pretty much, but what we want to do is to undo the whole process. So to undo the whole process, we have to start from the end. So if the last one was adding 3, then we have to subtract it. And that's something that reminds you how to, solve equations, for example. That's the same logic. So we really need to think, okay, we are undoing the process. So, okay, the last one was adding 3. Now we are undoing it. We're subtracting 3. That's what we get. Like we start from the beginning with the kind of new x to try to undo it. Then the first operation was multiplication by 2. Now we divide by 2. And this is what we get. So I understand that in other examples it might not seem as evident as here, but I think that this is a really nice way to understand the logic behind inverse. In the worst case, if you don't know how to get it and it is just for you to, I don't know, check something on your homework on micro, or just to, have an idea for the derivatives, you can use online inverse function calculator. So in the worst case, the getting the inverse function can be done like that. But what I wanted you to do here is to really understand the logic behind it. So this is an inverse of this, and we don't see it straight. So with the simple examples like 2x, yes, you understand that 1 over 2x will be the inverse, but here it's already more complicated to see it. Nonetheless, that's gonna be our answer. And this is different logic. So here what I'm gonna add as a caption is inverse function logic. And I also wanna show you one beautiful thing. Okay, wait a second. This will be the official form with the change of variables. This will be the mathematically exact, yes, because the notation, exactly, correct notation. That's how we do it. We don't change x to y. We change it for our convenience when we calculate it, express x in terms of y, that's easy. But here, this is how we're supposed to give the answer. And for your homework, you saw that I was saying, well, find an inverse, so f to the power of -1 of x, so the same parameter. And it really does not matter after all, because, you can write it, you can get the correct inverse function and write it different, it will still be okay. So don't worry much about the notations, especially now. We will worry about the notations and derivatives because there, yes, some things are super important and we should never confuse them. Here, both options are acceptable, especially in economics when it starts making sense, for example, as the demand function. Here, whatever, we leave it like that. And I think this is just the other way to show the mechanism of inverting functions. And another thing that can help you to verify if you got the correct one. So imagine you need an inverse function, you don't have the calculator, you are not so sure if you got the right one or wrong one. Well, there is a nice way to check it. So let's call it verification. Verification first with just numerical examples. So let's try to find an image of 4 by the initial function, so by 2x plus 3. So here what I wrote, an image of 4 by f. Okay, so what we're supposed to do, we're supposed to do 2 times 4 plus 3, 11. Then, okay, that's cool. Why did I take 4? Just because. it's absolutely taken from the sky. I could take 2. I just want to take some value of x. Okay, now what I want to show you is that if I take an image of 11 by the inverse function, so of 11, what do I get? I'm gonna get a fraction. So here I'll have 11 minus 3 divided by 2, cool. And that will be equal to miracle 4. So just solving the problem in general, right? You have function form, then you get function form, and you are not so sure. So what you're supposed to do is just take whichever number, really. I took 4, you could take 3, 2, e, and then you do the image of, you calculate the image of this number by the initial function, and then you calculate the image of the result by the inverse function. So what we're supposed to get is like 4 that is here. Oh, yeah. Let's take the ugly color. 4 that is here. You should get it here. And the 11 that is here. The result of the first calculation. There are no more colors. This is a good one. You will get it here. Okay, so that's with the numerical example, the simplest as always. Another thing, you could think of it in general. So this is verification numerical. And then we can think of a verification general form. Let's call it like that. So in general form, what matters? So we say that for every inverse, wait a second, I read it and then I say it. Okay, so if we take an inverse of a function that we had in the beginning, we're supposed to get just x. And it might seem confusing right now, so I'm going to show you with the example that we just did. And then I want you to try to do this verification in general for all the questions from the homework, and you'll get it. So this is something that you should really get by practicing. Otherwise, I can spend hours saying blah, 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 but you'll still not get it. So let's see. The inverse function, what does it do? It takes x, does minus 3, and divide by 2. Okay, so this is, I can copy this. And I want this, and this, even the writing seems messy, right? So this is what inverse function does. And as you can see, what we're trying to do is something like take an image of an initial function by an inverse function, but in general form with no numbers. That means that here, instead of x, I'm supposed to put the initial form of the function. So I'm not taking just x here, I'm taking the whole thing. And that is what it means taking the function of the function. So instead of x, I insert the function that is in the middle, so like the internal function. And then, I can see straight that plus 3 minus 3 will give me 0, so I end up with a fraction, fraction 2x divided by 2. And what is it? It's just x. So that's exactly what we were expecting to get. Anyways, so let's do something like this. This is a formula. Well, it's not super beautiful. but at least you see that this is something, the green stuff, is something that is always correct for inverse functions. And this is a proof. So we took our example, as simple as it is, but it works, and we got x in the end. So we were supposed to get x, and we got x. Perfect. This is great. So now we see. Homework. I think it was not that bad. I know how to check. Do you mind putting pluses if this explanation seems a bit better than what we did yesterday? Wow. Thank you. Okay, great. I hope with the minimum function we will get there as well. Cool. So now let's get to the homework. You have the well, I can actually, or can I can, right? Homework, new homework. That's the thing that we need. And I'm switching from showing just one window to showing two windows, and it's not going very well. Okay, wait a second. So I stop this, and then I'm gonna do a new share of just my screen. And just my screen for now looks like this, and then we do this, and this, and this, and this. Okay, look, this is better, this is better, this is getting better. Okay, whatever. Perfect. So now on the left you see the exercises, and here we're going to write the solutions. Oh, do you mind putting real quick pluses if you actually do see the exercises on the left and my whiteboard on the right? Okay, perfect. Cool. Thank you. Great. So, first one. Given g of x is equal to square root of x minus 3, we need to find the inverse. So you now have two options, right? So either you just go with substitute the letter and express one in terms of another, or you think of what does the function do and try to come up with a function that undoes it. On the first example, it actually is really better to do the logic of what it does, what it undoes. The second example, not at all, because, well, it does too many things at the same time. So we cannot actually, separate first it is this, second it is this. But let's try with the first function. So first function, function g of x tells us, okay, now you take your x, then you do subtract 3, and then this you take, well, what you get is x minus 3, and then you take a square root of it. And what you get is, well, square root of it, right? Of x minus 3. Okay, cool. So, okay, it all fits here. Perfect. Great. So now we need to think of a function that will undo it, and that will be something like g to the power of minus 1 of x. What will it do? It will first, what is the inverse of taking a square root of something? Well, it is a square in it, right? So let's say raise, oh wait, you're telling me something. Power 2, yes. Cool. Raise x, no, first, well, let's say, first we take our x, and then we say, raise it to the power of 2. Okay, cool. What do we get? We get x to the power of 2. X squared. And then the first action was subtraction of 3. So now we say, well, add 3. 3. And we get our x squared plus 3. Okay. Yeah, we got it. So I did it with a different method at home, and now I did it with this logic of inverse, and I received the same result. So I hope you got the same. Okay, because, wait. Some more questions about it, so I close the conversation and get to the explanation. Okay, so first of all, no, I cannot make a parallel. So what we should do is really start by just x. And here, what we did, we started by just x. We didn't start by 2x that we had in the beginning. And that's what I told you, from the outside, so when you look at two functions, like at this one and at this one, they might not look like, mirror. But the logic is always the same. So you first take just pure x. And then what you do is you take the last action and undo it. Then, okay, cool. And then you take the first action and undo it. So let's just do the verification, okay? So if you're not convinced, we can always take something like a numerical example. Okay, cool, perfect. But actually taking a numerical example here can be fun. So let's take 4. So verification. Let's take 4. Image of 4 by G is what? Is the square root of 4 minus 3. This is 1. Then image of 1 by the inverse is 1 squared plus 3, 4. Okay, we got it. I was a little scared that we wouldn't get 4. We got it. So that means that it works. So it's all perfect. Here we can clap and move to the next one. Okay, let's do homework orange. Great, so we could do the verification in general, but I don't want it. Another thing here is that before taking inverse, we were supposed to make sure that this function is a one-to-one mapping. And we could do it just by looking at it because it is square root and we know that square root is a one-to-one mapping, or plotting it. Now we move to the second function, and here it is the same. We were supposed to make sure that this is a rational function, so we're supposed to make sure that it is a one-to-one, and it is a one-to-one, so we can just move to getting the inverse. So here Wait a second. Yeah, technically we should, but we already start with a g that is a function. We know that it is a function, right? So we know that it's properly defined already. So it means that we know that it will be on the domain, the first quadrant. But the inverse does not necessarily have to always be in the first quadrant. And if we plot this thing, I agree that we're gonna get an extra, this is a parabola, so we're gonna get an extra branch that we were not supposed to have, since x was only greater or equal than 3, not 0, right? So I'm answering now the question of Menxin, and the inverse function only applies when x is greater or equal than 0 or than 3. So I think that you meant than 3. And yeah, technically it is right, but I didn't want to bother here with that, since we just need a functional form. Okay, so really don't worry about it. I cannot think of a trick that would catch you with the domain for the inverse. And good thing is always to plot them and make sure that they are actually symmetrical, with well, they are a reflection of each other if we draw 45 degrees line, and that's it. So you're right, and that's true, but don't worry about that for now. The inverse function of the inverse function is the initial function, because in this case we can do that because x is squared. Wait a second. How do you see so quickly without putting numbers to the question that it's a one-to-one mapping function? I'm gonna first answer to Elisa's question. I see it because I know how square root looks like, and in my yesterday's presentation I also showed you whatever we put inside the square root, it will always look like this, like you know, the thingy, an arc, and it will always be a one-to-one, just because square root is defined like that. We know the domain and range of square root yesterday. So yeah, here you have to learn, well, all the functions that I gave you in the presentation, well, you have to learn how to plot them. And then how to plot their modifications, like for example, not square root of x, but square root of x minus 3. And then you will know. Okay, so the inverse function of the inverse function is the initial function. No, the inverse function of the initial function is x. And the inverse function of the inverse function, I don't know what it is. It doesn't have to be the... Well, wait a second. So, I'm confused, so I don't want to confuse you. If I do here the verification in general form, will it answer your question, Antonio? Okay, let's see. So what we're supposed to do is take something squared and add 3 to it. Okay, wait a second. This is the inverse. So g to the power of minus 1 of g of x equals, so that is the inverse, and here instead of just x, what we're gonna put is square root of x minus So, perfect. When we put a square root back to the square, what we are getting? Okay, technically we get the absolute value of what was inside the square root, but well, square anyways is gonna be positive. So for sure we can be very glad writing here this. So this is this part. And then we had to add 3. And then we have to get x. And it worked because what we got was x. So I guess your question is if taking an inverse of an inverse will give us the same functional form that we started with. No, it will not give us the same functional form, it will give us just x. Okay, good? All good? Perfect, thank you. The second one, as I started saying, hard to think of what is the last operation that the function does because we have x both in numerator and in denominator. So let's go with this example. Let's do this. Let's apply the same logic as we used last time to do Celsius Fahrenheit. So I'm gonna say y, I'm gonna take the letter y, it doesn't matter. Y equals this fraction, x plus 4, 2x minus 1, minus 5. Okay, well, great. So now, pretty much express x in terms of y. Okay, let's start a little by little. First of all, we multiply both sides of this equation because it is an equation. We multiply it by 2x minus 5. Okay, so we get y times 2x minus 5 equals x plus 4, right? Good. Now what we have, we open the parenthesis on the left, so we get 2xy minus 5y equals x plus 4. So now we have to get x somehow. Well, let's group all x's on the left and all not x's on the right. So we still have this, then we do minus x, and that will equal to 4 plus 5y. Correct? Yeah, I think so. Good. Then now we can just factor x on the left. So we get 2y minus 1. And here we get our 4 plus 5y. Okay, great. Well, how do we get x? Now we have to divide both sides of this equation by 2y minus 1. And here we go, we get a fraction, and it looks like 4 plus 5y divided by 2y minus 1. Okay, it absolutely does not look like anything reminding us of this, and we cannot see straight that it's an inverse. And if I were to ask you, okay, just by looking at the equations, tell me if this is an inverse of this, and you will be like, well, no idea. So it's really like a calculation process, and even if it doesn't look like it, sometimes it is. So in here, to give the answer mathematically correctly written and noted, we can say, we started with, what's the name of the function? H. H to the power of minus 1 of x equals, it's of x, right? So x That's that. There must be a more rigorous technique. Well, I like plotting these things with help of the derivative. And first of all, I can put the intersection with axis. So I know that if x is equal to minus 4, h will be equal to 0. So I already get 1 point. I put it as an intersection. Intersection with the y-axis, with y-axis we don't have it. We have it, sorry. We calculated by putting 0 instead of x, right? So we substitute x by 0, blah, 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 we get some h. And then we see what's happening in the intervals in between, and I'll show you that. So we'll take a function that we saw on the yesterday, and we'll try to plot it without, not super precise, but schematically at least, so we can see the intersections with axis and how the function is decreasing, increasing, how is it convex, concave. So that already helps a lot, especially to check if it's a one-to-one mapping. All right, so let's move on, and this is an interesting part. So you see that well, let's write it. It's not that difficult to retype. Okay, so we have something weird. You're not gonna see this. You might see e to the power of x. That you will see. But 3 to the power of x, not so much. But I just wanted again to give you 3 because like this I can write a proper log with the base, and you recall what is it about the base of a logarithm. Okay, cool. So I'm saying a lot of so, right? In the recording I saw it. Well, I hope it's not too bothering. I'll try to say it less. We need to undo what? Again, it's really hard to understand what was done to x here. We can say, so x was taken, well, 3 was raised to the power of x, so x was, you see, there is a difficulty to define it. So let's just go by the same logic as in the previous example. If you master logarithms, you see what was done to x, and you can tell what's the answer straight. If you don't, well, it's okay. We say y equals 3 to the power of x. Now, how do we express x in terms of y? The same thing. How do we do it? Wait a second. Yeah, I still have a lot of space. How do we do it? We think of how to extract x on our right side. Wait a second. By logarithm, yes, but why and how? How will it work? So to extract x from here, I have to use the property of a logarithm that I'm going to write right here, and it will be in some green or whatever we choose. So we remember that if we take a logarithm base 3 of 3 to the power of x, what do we get? So we look at this thing and we think, okay, the logarithm is a power, is an exponent. So it is an exponent, it's a power to which I was supposed to raise 3 because it's a base to get 3 to the power of x. Well, to which power? To x. Okay, so this is something that we are using here. It's a property of a logarithm. And if logarithm didn't have this sweet property, we would never be able to solve it. So we understand, so what we have to do now with both sides of this equation, we have to take logarithms base 3 of both sides. Well, let's do it. In here we get logarithm base 3 of y. And in here we get x, as we already said that we get x. Okay, well, we're done. So now if you use the calculator, and if you want to choose and prove that your answer is correct, it will most likely give you something like x equals a fraction natural of x natural of 3. So why? Is it also correct? Yes, it is also correct. So the calculators online, the majority, they try to always give you the answer in terms of natural logs, because everybody knows that any other logs are not so widely used. So most likely when you ask for an inverse, you need something expressed in natural logs. I was not expecting you to get this. I was expecting you to get this. Yes, absolutely, you could. This comes from the property of logarithms, that is changing base. So you see this formula in Duolingo, you see this formula in my slides, and if you really want me to explain step by step how this turned into this, I can do it. You just have to send me an email. But honestly, it really does not matter. And as I told you already, most likely you'll see not 3, but e, and then your answer will be just natural log. So no need to worry. And let's give an answer properly. So it was function f, right? Yep. So our inverse. Equals this. Okay? Is it good? Just put pluses if it's good. Okay. And if you're not putting plus, then tell me what is that you don't like. I understand that this format of using Zoom conversation can also be not very great for learning, because when I ask you to formulate a question, it takes time, and maybe I don't wait enough for you to type your questions. But I'm trying to see where you are. So in the worst case, you should just write something on your notebook saying like, ask about this, and then either send me an email afterwards or type this question in the conversation, and if we see it later, it's not a big deal. I think everybody understands that this can happen, and I can get back to a certain point in the lecture. Cool. Why is it not logarithm of y equals to logarithm of 3 to the power of x, which makes x first of all, this is supposed to be y, obviously. I just confused letters here. I'm trying to understand Elise's question. Why is it not logarithm of y? Okay, so okay, that was that. You're good, thank you. Okay, great. Now I think we can move on, and we'll see a beautiful example of a natural log, so we don't have to deal with these bases anymore. y of x equals natural log of x plus 1. So I'm going to write it straight in the form of y equals to an x plus 1. Here, the letter y that I always use to do the inverse coincided with the initial name of the function. It is a coincidence, and well, you can take any letter. Here we could take a letter L, for example, and be happy. So, okay, now guess what? We have the same task of expressing x in terms of y. Okay, how do we extract x here? It is inside a log, and we also added 1 to it. Maybe the going through the logic of the function can help, so we can say, well, the first operation was adding 1 to x, and the second operation was taking the natural log of that expression. We can think that way, or we can try to see like we've done for the two previous examples. So let's go with the express x in terms of y now. And how do we get x out of it? First, we're going to use again a beautiful property of logarithms. So I'm going to write it here and also highlight it in yellow. Yes, like that. So e to the power of natural logarithm of x. What is it? Oh, you're replying. I like it. E1 x. I like x most. Why? Because what is written here? So e is raised to a power of a power to which e is supposed to be raised to get x. So here the exponent here, like the indicator of exponent, is saying this is the power to which we're supposed to raise e to get x. And now we're raising e to that power. Well, what are we getting? We're getting nothing but x. And these two things are beautiful. So this is, well, it's all about the same, right? So this yellow, let's call it formula, and this yellow formula, this helps a lot, believe me. Now, we say, okay, we need to raise e to the powers of both sides of our equation. That will not change the equation, so the equation will still hold as true. So what am I doing? I'm gonna write it and you'll see it clearer. I'm saying, okay, both sides of my equation are gonna become powers of e. Okay, great. Why did I do it? Because I know that now this right part is just x plus 1. So here we have up equals to x plus 1. Okay, great. So we just need to say that x equals to e to the power of y minus 1. And here, understanding the stuff that I was explaining in the beginning of the class is important, because what we said, so I was trying to also go through this way right now solving that. So we said, okay, let's think of what does this function do. This function first adds 1 and then takes a natural log. So it's very logical that in the end we got minus 1, because we had to undo this first action of adding 1. Okay. I think it's fine. So if you still have troubles with this exact example or with inverses in general, you should ask me about it, formulate your question, and I'll try to help you with that. Okay, so now before, what if I do like this? Okay, before going to this find an image of find an image of find an image of I wanna go back to minimum function, and I really hope that it helps you. So this is our new screen that I'm gonna share. Okay, cool. So I'm supposed to share the whole screen, so you should see this window as well. Do you see the Word? Well, it's not Word. It's whatever weird thing that is for free. Okay, cool. Thank you. Okay, so it's gonna be tricky. First, I wanna start with wait a second. Okay. I'm gonna start with an economic example. So what is happening here is a consumer. A consumer, Lisa, always drinks 1 cup of coffee always drinks 1 cup of coffee with 2 cookies. Perfect. So the idea is that there is no coffee if we don't have 2 cookies. So if we have just 1 cookie, okay, does not work. It has to be a bundle. So if I just have 1 cookie, I'm not gonna drink my coffee because 1 cookie is not enough to enjoy the coffee. That's the logic. Okay, great. So let's now denote X number of cookies and Y no, I don't like it. I did it different. It really doesn't matter, but I just prepared it the other way around. So here X is number of cups of coffee. Okay, so my utility function obviously will be, when you see this framework, now without even thinking of it, you should tell me that the utility function will look like, first of all, it's a function of 2 variables, x and y, so it's a multivariable function, and it will be a minimum of, so here is the trick. A minimum of what? 2y and x or 2x and y? Please type me your options. Who thinks what? Good, good. 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 All last options are mistaken. Okay, let's go and understand it. So this is really something that every year we struggle with, and I struggled with it too. So let's imagine that what I have here is 2 cookies, right? So how many cups of coffee, the minimal that I need? is 1, right? So we know that this is x and this is y. And well, to get our minimum, what we need, well, I cannot say 1, I cannot say equal, I can just try to, do it like that. So let's go to the plot. Okay, so before thinking of how it works, I want to just plot these dots. So if I have 2 cookies and 1 cup of coffee, what's gonna be my utility? My utility is gonna be 1. Okay, so wait a second. I wanna just plot it on the, how do I do it? I was like, I trained. I did actually. Wait a second. So we put it like that. Okay, great. So my first dot will be on the level of x equaling 1, because that's 1 cup of coffee. And then, yeah, and then y equaling 2. Why am I doing it like that right now? Because I just want to understand what is the minimal amount of, number of stuff that I need to get at least to enjoy at least 1 cup of coffee. Well, that's gonna be our dot. So this is our dot. I don't know how to do dots, but I came up with this option. So this is the first dot that for sure belongs to this graph. Why do I say that it for sure belongs to this graph? Because what I have here, for example, if I want to find this dot, does this dot belong to a graph? Wait a second. I want to make it pretty. Okay, this dot here. It does not, because I'm not consuming anything. I'm consuming 0 if I only have 1 cookie, right? So y is cookies, x is coffees. So I'm saying, well, this dot that is in intersection here corresponds to a situation where I have 1 cup of coffee and 1 cookie, but it's not interesting me at all. I don't want that. I'm consuming only 2 cookies per cup of coffee. So this dot does not belong. But we know that this dot does belong. For sure, it's a bundle. Here, we established our first bundle. Okay, let's think now of a second bundle. Where will the second bundle be? So if I want a second cup of coffee, here, I need to ask now for 4 cookies, right? So now I'm gonna be somewhere 2, 3, 4 here. Okay, so let's note it as our second dot. This dot for sure will belong to the graph, unlike this dot, for example. Shady dot, it does not belong to our graph, and it does not correspond to a feasible situation. Okay? Okay, so now you see what's happening. Now you see that, well, it looks like a sequence. So let's put another line. Let's say, okay, cool. So let's say that now we want to consume 3 cups of coffee. We have to ask for 4 or for 6 cookies, right? Here. Okay, perfect. So now we're here. Great. So first tell me if so far you understand how I place dots on a graph. Just do plus. Okay, placing dots on a graph makes sense. You could tell me, well, why is it exactly these dots? Because I know for sure that they belong to the graph. At least something that I know for sure, right? And here, now we have to figure out, okay, what else belongs to this graph? Let's start from this initial point. We say, okay, so now I'm consuming 1 cup of coffee. So, to the situation of 1 cup of coffee, to this situation, all these options of y will correspond. Why? Because, well, I need at least 2 cookies to consume 1 cup of coffee, right? And that works. That is going to work for me. So here I'm having good, perfect. The same, well, 2 cookies, I can think of, well, I can increase as much my consumption. No, that's not beautiful. My consumption of coffee. And still enjoy 2 cookies. I just need 1 cup of coffee to enjoy 2 cookies, and the rest, well, it's good if I have more, well, it doesn't matter if I don't. Now, this will apply to the other levels. So, wait a second, don't ask me questions yet. So that's going to look like this. You can be plotting at the same time too, so you don't hate me right now. Oh, that's better, right? Okay, cool. So the last one. And then this. Perfect. I just drew 3. So the question here should be not more like, why is it like that? The question that helps you to understand is, why is it not like that? Why cannot I draw a line that would go down here? Right? So that's something that corresponds to 3 cups of coffee and less than 6 cookies. I cannot, because I'm not going to consume that. I'm going to say, not consuming 3 cups of coffee if I don't have 6 cookies. And the same applies to the other way around, the logic of, well, I need at least 1 cup of coffee to enjoy each 2 cookies. Great. So now let's see. First of all, you already can figure that there is this line that goes like that, and it goes like that just because 1 cup of coffee, 2 cookies. As simple as that. Let's make it fatter. Okay, perfect. So the equation of this line is, if I want to express it in terms of y, so like normal mathematical thingy, I'm gonna say y equals to 2x. I think you should know how to get this. I hope you do. If you don't believe me, you can just check it. Okay, perfect. So now it starts making sense. So to provide at least 1 bundle per each x, I need 2 y. So that means that per each y, I'm gonna need, there is no such a thing, okay? So you should not think this way. You should just plot the dots, all right? So just plot them and see what's happening. What's happening here is that this line that will provide origins for all our L curves is y equals to 2x. Okay, so y equals to 2x. Great. Now the last thing to figure out is what, after all, are we writing here? Do we write 2xy or do we write 2yx? Well, we write 2xy. First of all, this, once you define the line, it gives you a clue to what put inside of the minimum function. But we should just think of it logically, right? So let's think. So the first utility thing that I drew, the first utility, wait a second. We can even write minimum. Mathematically, yes. Economically, in this case, we cannot write min x y over 2 because that will mean something like a half cup of coffee. And we don't do that just because we have a discrete case. We don't have continuous case. But in a continuous case, purely mathematical, that works. If we reverse, after all, our graph and make x dependent variable and y independent, that will be all right.